Hello there everyone, my name's Bryden. Before we start, I'll just call out all of the sponsors we've got today. Without them, this event wouldn't be possible. Okay, so I'm going to be talking about some of the sort of top database performance techniques that I've come across over my career. I spent 20 years writing database performance monitoring software, so most of the techniques we're going to see here come from seeing what my customers were having trouble with. And it's a bit of a spoiler, it's all pretty simple things for 99% of your database performance problems. It's something really, really silly and really, really easy to find. So right at the end, we'll have a hit list of things you can look for. Okay, so today you can go and talk to all the sponsors and play bingo, and there's some great prizes on offer, so get into that in the breaks. So this is a little bit about me. As I've said, I spent 20 years writing database performance monitoring software, so I have seen an awful lot of what goes on inside databases and what people do wrong with them. Now, because I'll move fairly fast through some of this stuff, and some of the techniques you may want to read back on, you can get this at this location. I'll put that up again later. That's just so that you don't feel you have to grab everything while I'm talking. So what are we going to cover today? First, we're going to cover a bunch of things you can do that will generally improve the query performance when you're using your database. We'll see a lot of demos, and most importantly, it's all simple techniques, stuff that as a developer, not a database professional, you can add into your own code and make these improvements yourself without pretty much any effort or very minimal effort. And finally, I'll show you how you can measure the improvement and how, if you get a DBA involved, how they would measure the improvement. And it's also really simple, so you can do this yourself and understand how to measure the difference between, say, two queries you're going to try, which one is actually performing better. Okay, so let's start with first a quick little useful trick. I'm talking with respect to SQL Server today, but everything here, there is an equivalent in all of the major database, relational database engines. So in SQL Server, if you want to get statistics on your query and know how much work it's doing, you can add this before you run the query. So set statistics IO on, and it will return you a whole bunch of statistics when the query finishes that allow you to understand how much work it's actually done. And we'll see this in all the demos, and there are quite a lot of demos in here because the idea is to let you see how you can measure this stuff more than the tips. Okay, so for the examples today, I'm using Stack Overflow's question and answer database. So they've got it publicly available, so I've downloaded it, and it's up to about 2013 because that was a nice size to work with. And at the end, I'll show you where you can download that from, particularly if you're using SQL Server. There's a database you can just download. Any other database engine, you've got to download the raw Parquet or JSON files and add it to your own database. But SQL Server, you can just download it ready to go. Okay, so on to our first technique. And this one may seem really obvious, but so many people don't think about it. The first one is reduce the size of your tables. Make sure you don't have as much data, more data than you need. And why is this important? Well, large tables take longer to read and update. They also take up more buffer space, and buffer space is the cache on the database server in memory where it's keeping pages of disk in memory so it can quickly execute your queries. So if you've made your table bigger and it's having to read and write more pages of that, there's less other things in your cache. So the more you can reduce the amount of stuff in your table, the better. So we know we want to reduce the table size. What can we do? The most obvious one is archive unneeded data. And I'll give you an example from a client I had. They got me in and said, our database queries are performing appallingly. We've got 23 years of transaction history in here. Why is it so bad? And the first question I asked them was, okay, you're only reading this with an application. How far back in history can your application go? And it turned out they could only read up to 6 months history. So they had 22 and a half years of extra data. So all we did was archive that out to somewhere else that they could use for reporting, and suddenly their query performance improved by about 1,000 times. Because of course, everything was fitting in the cache now, so you're getting like 99% cache hits instead of it was about 12% cache hits. So that's the sort of improvement you can get with some of these techniques. And they're not hard to do, it's just a bit of thinking. The second one is reduce the size of columns. And the most common thing here is having fixed size strings. So I've seen ones where they've done 512 wide strings, 512 character strings, and they know it's going to have a constant in it. And it's, a status, like a transaction status, approved, shipped, and it's only like 20 characters. Why not make that a 20 character string, and then your database table gets much, much smaller. The other one is, say, things like prices, putting that in an int64. If someone can afford to buy something that's expensive enough that the price fits in an int64, you're probably doing very well, and you can probably afford the extra storage. The other one is, when you go and look in people's databases, they always have far more columns than they actually need. And a lot of them are what you could call computed columns. So you get things like, you've got, in a transaction database, you've, say, got the cost price of the item, the number of items that were sold, and then if they're just going to multiply those two together, they'll then write the total price in there as well. That column's completely useless. The only thing you can get out of that is rounding errors. Okay, so here's a quick example of how we measure this stuff. So for this example, we've got the votes table. So this is how many votes people have made against various answers in Stack Overflow to tell which is probably the best answer for you to choose. So a lot of the time you want to know the most recent votes. So I've taken the votes table and then I've pulled out the most recent 1,000 votes, and then we're just going to grab all of the data out of both of those. You'll see I'm setting statistics.io on there, and now we're just going to run that query. You'll notice I'm doing this as a video, because if you look down in the bottom right, it tells you how long that query took. So that took 2.5 minutes for the second query to run. That's why this is all done as a video, because it's not really practical to do here. But if we go across to the messages tab there, this is where we get our IO statistics returned. They're returned as messages. And the key numbers to look at are these logical reads. So you see we've got logical reads and physical reads. The difference between a logical read and a physical read means the database server went to disk and read something. A logical read is it went to the cache, said, have you got that page? And sometimes it'll have to go to disk, sometimes it'll just come back. If it just comes back, that still counts as a logical read. And the reason that one's more useful is that typically you're doing this on a development server, so you're not getting everyone else, flashing pages out. So if you run the same query 3 times, suddenly everything becomes logical reads because it's just sitting in your cache. So that's why always when doing this stuff, look at the logical reads, not the physical. Now, if we look at that one, you'll see we did 16 logical reads for one of them and 250,000 for the others. So, that's a huge improvement. And those two numbers are, in terms of execution time, are literally are linear. So the less reads you do, the less time a query takes to execute, because doing reads is actually what database servers typically spend all their time doing, is sitting there reading data off a disk or out of a cache. Okay, so the second one, and this will also seem kind of obvious, is when you're doing a select statement or anything else, only specify the fields you actually want out of that table. Don't do select star from as I did in the previous example, because that means it's got to go and read all of the columns. And if you've got indexes, that can sometimes cause you to read stuff out of an index and the table. And we're going to go to an example that shows exactly that. But first, the other thing that happens here is if you have to transmit all of those, say you're returning 10 columns instead of 5 and they're all the same size, you're transmitting twice as much across the network. And of course, you're spending twice as much CPU encoding the packet from the database server to send to your end, and then you're probably marshalling it at the other end into something else, probably reading it into some variables and then pushing it up through your stack. So you've spent a whole bunch of CPU reading those extra columns out and getting past them, even though you were never going to use them. So that's why you get a bunch of benefits, even more than just the stuff, the obvious of reading it from the disk. So for this example, we're going to look at the users table, and we're just going to grab the display name and location. So we're going to do select display name location from users, and you can see that about halfway down. But first, what we're going to do is create an index that only contains display name and location. And what that'll do is the server will actually just read the display name location index and return us that. Return all of the data from that. It won't have to look at the main index which has all of the data in it. Now, you may notice I clicked up on the toolbar there. That was adding an extra thing called include actual execution plan, and we'll have a look at the execution plan once it comes back. Or maybe I didn't. Oh no, here we go. So you'll see there's actually 3 tabs this time. We've got the results, it gives us some messages back, and it gives us back an execution plan. So what's an execution plan? It's a graphical view of the steps that the database server took in trying to fulfill your query. So you can see in the first one, it did working from right to left. It did a clustered index scan of PK, which is the primary key, so that's the main table. So we went and read all of the data out of the main table, which is what we expected that first one to do because it was select star. For the select display name location, it just did the same thing except on index display name underscore location. And if we look at the logical reads, we did 45,000 logical reads for the first query and only 13,000 for the second query. So that would typically mean it took a third the time for that second query, which is a pretty good improvement for just changing the number of columns you're picking up. But that one's slightly contrived because we've got an index, but you will get at least an incremental improvement with that change. Now, the third technique, this one generally gets you the biggest wins, but it takes the most effort. It also requires a lot more understanding of what's going on, but it can often make things like up to 1 million times improvement in performance. So I'll give you an example here. I was transferring data for a customer and they had 40 years of data accumulated, and we sort of went through and I just took the data off. We didn't do any indexing and we had to transform it and then load it into their new system. And we did a test and worked out it was going to take about 36 years to actually get that data in. So we were oh, well, maybe we should add some indexes and try and improve this. And using the techniques, just a few standard techniques for index management, we got it down to 8.5 hours. So it was actually viable to get their data migrated into their new system in a timely fashion that was all done over a weekend outage, whereas they'd been starting to think about contingencies of what they do during the months, if we only got it down to months where this system was being migrated. That GitHub repo I mentioned before, I've got another presentation in there that just covers how to do indexing. So I'm not going to cover more than telling you that it will make a huge difference here. But that brings us on to the fourth thing. Verify that your indexes are actually being used, because the number of times people create indexes and then you come in and they're complaining that their database is running slow, and you test the query that they wrote the index for and it's not actually used, is extraordinary. So in SQL Server, the most obvious thing to do is if you can just run the query and you know what it is and it doesn't require, data out of something else, you can just run it in SQL Server Management Studio. Do that with show actual execution plan on, and then you can check that it does do what you expected. As we saw in that previous example, you could see which index it used and for what. But what about if you can't do that? The second thing we can use is write a query that can tell us what indexes aren't being used. So let's take a look at an example of that. Now, what we're looking at here is the query we're concerned about is select star from DBO posts for the 22nd user. And just as an example, I've shown you how to grab the actual execution plan, and you can see it uses a non-clustered index, and then it goes back to the main table and grabs just all the columns for the rows it's identified. And it's quite efficient. But how would I tell that that's actually occurring if I couldn't work out what the query was running underneath? What I can do is run a query like this. And we're looking at sysdb index usage stats, which is what's called a dynamic management view. It gives you usage stats for each of the indexes. So what we can do is execute this query, and then in this example, we'll then run the small query we've got, and then we'll run this query again and look for the differences. If you're doing this in a production environment, you might do this by running it, then running your workload, go and get a few users to log in, wait for things to happen, and then come back and verify whether your indexes were used in the workload that you expected. And we're about to run that query here. And so you'll see in the results, what we've got is it's found 2 indexes that have been used. There's one on the posts table and one on the users table. Now, we were doing a select on posts, so let's look at the difference between the first run, which is that top grid, and that bottom grid. It tells us what the index name was, then it tells us the index ID if we ever want to go back and find that index definition. It also tells us how many user seeks, how many user scans, how many lookups, and how many updates have occurred on that index. And those numbers are since that server started. So they get reset every time the server starts. So that's worth bearing in mind, that they will reset. But you'll see our user seeks went from 1, then we ran our query, and then there were 2 user seeks. And because nothing else is running on the server when I was doing this, I know that that 1 was due to my workload. So my workload is in fact using that index. So that's how you can work out whether the queries you expect to use things are in fact using those indexes. So if you go and build indexes, do something like this to make sure those indexes are being used. because that's probably the second biggest reason why performance degrades over time. Suddenly the server stops using your index for whatever reason. Okay, another thing that often causes problems is implicit type conversions, particularly in where clauses. And they can make the database server, instead of going and seeking to the exact row, so in other words, looking it up correctly in the index, it can end up where it goes and scans the whole table because it can't figure out that there's an index there, or the index doesn't match what it's expecting. So let's see an example of that. So what we've got here is we've got a table called vote string, and it's got a post ID column, which happens to be a string. So that first select there, it's going to be able to use the index that's there on vote string, on the post ID column, and go straight to it. The second one, it's got to go, it can't figure out whether a string value equals 99997 easily. So it's got to go through every single row in that table, convert it to an integer, in case there were things like commas in that string and other things, so it can't know exactly what looks like 9997 or whatever that number was. So it's got to convert every single one of them to an integer and then do it. And if we look at this actual execution plan, the one that we've scrolled past, just did a simple seek. But this second one has done an index scan, and then that parallelism piece that's second from the right, is it using the CPU to convert every single string in that column to an integer, and that took 2.5 seconds to do that. And then it's worked out which ones it needed and gone and spent a couple of seconds bringing it back. So that's the sort of level of thing you can see. And here's the I/O stats for that. So we did 20 logical reads for the first one, where we had the correct where clause. We got the type correct. We did 192,000, where we just getting the type wrong. So it's worth coming, if you're seeing numbers where it's taking way longer than you expect, that's one that's really worth looking at, is your where clause the same type as the data in the server? Because that will really, really hurt. Another one is avoiding looping. Now, looping is bad because in database servers, the loops execute one after another. They cannot be parallelized, typically. Some of the server engines are trying to optimize so that they can, but in general, they will operate 100% serially. And most of the time, the stuff you're doing in looping is an aggregation, and there's built-in stuff to do the aggregation for you, as we'll see. It's also worth calling out sometimes there are reasons why you need to loop. Like if you need to go and summarise all of the stuff in a given database and do that in each of the databases, a statement can only execute in one database context, so you do have to do that one in a loop. You go around each of the databases. But that's something you should very, 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 very rarely have to do. So there are other cases where you have to do it, but again, they should be very, very rare. Okay, so let's see an example of this, and it's worth calling out that in this example, when we work out what this code does, it simplifies immensely. So what we're going to do is we're going to fetch out of the posts table, and for each post we find, we're going to increment the number of posts we've got, and then we're going to take the total answer count and add the answer count of the row we're at to that. And here's the simplified version so that it's much more readable. basically we were getting select, count, answer count, and we're also doing the maximum of the answer count. And what we're trying to do in the top one was we're actually just trying to get the average number of answers for a given query. But if we look at the IO stats here, what we see is each one of those is each row one by one going through, and it's doing a couple of logical reads for each one. That last one did, it's quite a lot, isn't it? It's 4 million, almost 5 million logical reads. But if you allowed that top query to run, that one actually, when I did try it and left it overnight, that took 14.5 hours to run the top query. It takes about 8 minutes to run the bottom query. So it's a huge difference doing it where it's genuinely just doing the IOs and it can read ahead, so the disk is doing read ahead and knowing what's going to come next. The top one doesn't do that because it's not reading contiguous blocks. It's doing tiny reads and it doesn't realise that, you know, the next read's going to be the next block and so on. The bottom one will just read, you know, huge chunks out of the table into memory all at once, and then another chunk and another big chunk. So it's much more efficient. Okay, now here's the first one that developers really struggle to understand. When you write code as a developer, if you use an AND or an OR, it's pretty much the same efficiency, isn't it? Like, there's not a big difference, not a noticeable difference. Have a think about what a database has to do if you do an AND or an OR. If you do an AND, what it can do. So if you'll say, the example I've got for this is quite good because it gives you an idea. But if you're doing an AND, say we're grabbing, we'll go and look at the example. So here we're looking at users where their location is in the USA or they've got 5 downvotes. So to do that as an OR, what you've got to do is go and look at the user table, find all the ones that are in the USA. Then, because you're ORing it, you've also got to go find all of the people who have 5 downvotes, and then you've got to union the two. If it was an AND, you'd go and find all the people who lived in the US or who had less than 5 downvotes, and then out of that result set you got, you would use the other filter, and the server would actually work out which one of those it should do first, knowing statistically how many of each, you know, the spread of stuff in the index. So it's actually really smart. The other thing here is that if you're doing an OR, if we look at that top one versus that bottom one, you actually get a performance difference, even though they're doing exactly the same thing underneath, or you think they are. So you'll see that the server has optimised the second one, and it does 499 logical reads in total, whereas it does 1,600 in the top one. And that's because it's not very good at optimising an OR statement. It will actually expect the person writing the query to break it into and turn it into a union, and it will optimise that reasonably well. It's still nowhere near as efficient as doing an AND, which would be probably a quarter of that again, depending on what the distribution of data was. But just replacing the first query with the second query, the optimiser is optimised to optimise union statements way more than ORs in a where. Okay, and here's another one that seems counterintuitive. If you've got wildcards at the start of a string filter, so like %Fred, so in other words, it ends in Fred, is really inefficient. And the reason for that is if you've got an index of those strings, it's going to be trying to look it up on the first character of the string, then the second character. So it's going to be going through it the way you would a book index. But it's really hard to find stuff that ends with something using a book index. So it is orders of magnitude more efficient to, if you know you're going to be doing that pattern all the time, to actually reverse the strings and write a second column in there that's got the string reversed and create an index on that. And let's have a look at an example of that. So the first thing we're going to do is look for posts where the title starts with Y, then posts where the title ends in the word statement, and then the third thing we're going to do is there's a reverse title column in there that's been added, and it's got all of the titles backwards. And then we can do like reverse that piece of string so that it's finding starts with T, then N, then E, and so on. And what we'll see is there's a very different performance profile between them. And it'll take a little while for this one to run from memory. Yeah, and there we go. We've got the data back. And if we go and look at how much work we're doing, you see the first query took 2,000 logical reads. The second one, 103,000 logical reads, which will be every row in that table. So it's gone and read every row in that table. And then the third one, which is actually doing exactly what the first one did, but we've reversed the strings so it was more efficient at being able to do it. And it used the index. It did it in 120 logical reads. We made close to 1,000 times performance improvement just by reversing the string, knowing that we were always looking for stuff at the end of the thing. So if people know the last 4 digits, a common one is if you've got credit card numbers and the user types in, the last 4 digits of their credit card number, if you have to look that up, keep it reversed, keep the credit card numbers backwards as well, so you can do that search easily for them. Okay. This one is more for the older developers in the room. This is pretty much use join when you're doing a statement and not where. And I'll show you what that looks like, because these days you don't ever see anyone doing this except the really old developers. And the key thing here is that the optimizers these days optimize joins much better than they optimize a where statement. So if anything you can get into a join and you're joining 2 tables together, you're much better off. It's also easier to read, as I'll show you in the example. So if we take a look at this, what we're actually trying to do is show you the comments, the posts and the users. So we want the user's name and how many comments they've made and what the creation date of that post was, where their location is in the US. So the filter is location is in the US. So that should go in the where clause. You'll see in the first one, we're also got a where only user ID equals ID. What that's doing is joining the user table to the posts. In the bottom query, we've explicitly done it, and it's called it a join. And the other advantage you get doing the join like that is you can do outer joins, inner joins, which allow you to control what happens. If there's not data in the left side or the right side matching, you can actually control the behaviour, which is much harder to do with that top statement. But the other thing you'll see is that there's 3 statements there. Now why is there so few statements? The top 2 ones are actually No, I don't. I've missed some of the I/O there, I think. Oh no, the first one's getting it out of work table. So you're not doing that many less in the second one. It's about 300 less over 5,000. So you're talking 5% improvement. But that's 5% here. Other times you will get much better mileage. The thing, for me, the other reason to do it is that ability to control the null handling effectively of what happens when rows don't match. And it's much easier to see what's joining tables together and what's actually filtering your data like this. So there's huge advantages here. Okay, and our 10th technique, and this one really does apply to developers. They make this mistake constantly in code as well as databases. If you're .NET devs, which I am, they'll use count is bigger than 0, rather than going any, which means have I found a row? And the reason this is efficient is that exists, or any, short circuits out as soon as it finds the first row that matches. So it's going along, it's evaluating everything, and it's short circuiting as soon as it finds a match. Count goes through every row and comes back and tells you how many rows matched. So it's got to go through the whole table, or, you know, the whole filtered table or whatever. So they're the ones that don't work very well. The where count is greater than 0. Where exists is far more efficient. If you just wanted to know, for instance, has a customer bought anything from me? You quite often see people say, write that as where transaction count for customers greater than 0, instead of effectively the second one saying, does the customer have a transaction? Which was what the question we were answering. Okay, so let's see a quick example of that and see how much more efficient this can be. So what we're going to do is try and count all of the posts where they begin with Y. So where the person has asked, why does something happen? And you'll see we got quite a lot of rows, 10,000 rows matched that. And to do that, it took us 1,773 logical reads to work out how many posts there were with Y. It only took 4 to do the opposite, to find the first one. The other thing we're going to do is look at the negative case. What about if there was no rows that were going to match? Do we get any improvement then? And as you can see, looking at that, there's almost no change. And in fact, it was slightly more, it is one less, but it's basically the same if nothing matches, but just because of the advantage when you do find a row, it's worth doing anyway. Okay, so that's the top 10 techniques. If you download the presentation I've got from GitHub, that's got another 5 bonus ones. But we've only got 45 minutes today, so I had to cut a few out. So let's recap. These are the 3 big ones that almost every database server you go and look on, there will be something out of these 3 that you can do and get a large improvement. So we should reduce the size of our table in whatever way we can. Make columns smaller, make the number of rows less, don't keep data that we're never going to use, all those sort of things. Second one, only ever select the columns you want. And ORMs, which a lot of devs love, have a tendency to grab all the columns unless you explicitly say which columns you want. So be aware of that, because that's where developers start introducing that problem into their code. The third one is create indexes, and I'll give you some some more information on that in a minute. The fourth and fifth ones were verify your indexes are used and avoid implicit type conversions. If I was a sort of dev lead, I'd be asking my devs to look at these 5 first and foremost if we're starting to see some sort of degradation. Almost certainly you'll be able to get yourself a significant improvement. It may not be enough, but at least there's a reasonable chance that will get most applications past their performance problems. Then we've got a few others. Avoid looping. Normally that's someone who hasn't thought through how to do something and hasn't thought through how you could do it via an aggregation. But there are times where you do need it, but you need to be aware that that's probably going to be an inefficient piece of SQL, so you may want to try and avoid running it during business hours. Use and instead of or if you can. So think about your logical notation and see if you can turn it into an and. Avoid wildcards at the start of filters. That's a huge one if you've got that. It's not as common to end up in that problem, which is why I've got it a bit down the list. But if you do have that problem, that's an easy win. Using join over where, I think that's more of a readability improvement as well, but it does have some improvement. And then we've got use exists instead of count, and that quite often gets you a big win. So using any if you're using EF core, I can't remember that other languages, ORMs, but there's the same sort of thing there. So here's a few more. Avoid doing select distincts because that forces the server it can't spool it out to the data out to you until it's got all of it. So it's got to assemble it all in memory and then try and work out and then send it back. Because if it's already spooled out a whole bunch, it doesn't know if the values coming in is already in that stuff it's already sent you. So that can be quite inefficient. This is the one that most people know, is try and avoid doing huge writes. Or if you do, use typically there's a separate library. Like the SQL Server, there's the bulk copy library or the bulk insert library. Use that for large writes because it does a bunch of optimizations to make your writes more efficient. Another one is that some people think you can just keep joining tables endlessly. At about four tables to 6 tables joined together, and definitely anywhere beyond 6, the optimizer will give up on optimizing your query. So it'll get horrendously slow and it won't use indexes and you get all sorts of problems. So try and avoid joining more than 6 tables. Sometimes you might read the data back of joining 6 and then grab the other things based on what you got back from the first one. And then we've got use top for sampling, so don't go and just grab all of the rows when someone's got a production issue. The worst thing you can do is come in, do select star from users just to see what the users table looks like. Do select top 5 from users and see what the users table looks like. Often people do that under stress, and just the select star from users may be enough to turn it from bad situation to catastrophic. Use where instead of having. So having is a way of filtering the data that you get back in a query. Where is filtering as you go, so I'm filtering out the rows of the data. Having is a post filter, so typically you use that if you're aggregating a whole bunch of data and you wanted, people who I've sold to who have more than $1 million in sales. I can't do that until I've aggregated. But be careful, try and avoid doing anything that you could have done in the filter, having. So it's quite often you would have a where, which is doing the filtering, and then use a having to filter the outgoing data afterwards. and use pagination where appropriate. So often people retrieve all of the data to show page 1 on their UI and then do it again for page 2. That's a huge one to avoid. Okay, and now we've just got a couple of resources. Brent Ozar is probably the most understandable guy who lectures on database performance and databases in general. My company has a bunch of rules on how to improve database performance. Most of them are based off what's in here. That's where to get the database that we had a look at there. And then I've got one article I reckon in particular that's worth seeing, which is Brent Ozar's training that he calls it Think Like the SQL Server Engine, and he teaches you how the engine actually executes your queries in a very easy to understand way. And for so many people, the light goes on and they go, oh, I understand why this query would be really slow, because it's going to have to go and do this. So he's teaching you, using the analogy of book indexes, how it all works. And thank you again to the sponsors, and thank you for listening to me.